Now let's do some examples on application of the ratio test. So test the series. So solution for this. So we use this ratio test. With an given by -1 raised power n power 3 divided by 3 power n. So we can define an plus 1 as -1 n plus 1 n plus 1 power 3 over 3 raised power n plus 1. Now let's get the absolute value of an plus 1 over an. So this will be given by the absolute value of this. We have -1 n plus 1 n plus 1 cubed divided by 3 n plus 1. We are dividing this by -1 power n cubed over n 3 power n. This is just by definition. And then this one is the same as -1 n plus 1, and then n plus 1 cubed over 3 raised power n plus 1 times the reciprocal of this 3 power n over -1 power n, and then n power 3. Now using loss of indices, we'll have, so this is -1 raised power n, -1 raised power n power. So this minus this one just gives us -1 raised power 1 n plus 1 power 3, and then over. So here we have 3 raised power 1, and then n cubed. Then absolute value of -1 just 1. So this will be given by the value of n plus 1 cubed, and then times simply over 3 times n cubed. Now, which is the same thing as 1 over 3 into n plus 1 over n power 3. And then that is the same thing as writing a third into 1 plus 1 over n raised power 3, which approaches a third as n approaches infinity. And then the third, and this is what you can solve. As n grows large, so then this becomes a very small number, so then just becomes a third. And then this a third is less than 1. And that's by the ratio test. The given series is absolutely convergent. And therefore convergent. And then another example. Test the convergence of the series n power n over n factorial. So solution for this, so since an is given by n power n over n factorial are positive, we do not need the absolute value sign. Or absolute value of a positive number is just a positive number. So therefore, an plus 1 over an will be given by n plus 1 raised power n plus 1 over n plus 1 factorial divided by n power n over n factorial. This will be given by n plus 1 into n plus 1 raised power n over n plus 1 n factorial times n factorial over n power n. And then that is the same thing as n plus 1 over n raised power n, because this and this cancels out, this and this cancels out, which is the same thing as 1 plus 1 over n raised power n. And this is what defines the exponential number as n approaches infinity. And then since exponential is roughly 2.71 is greater than 1, then the given series is divergent. By the ratio test. The last test on convergence and divergence of series was what we call the root test. So A if limit as n approaches infinity of the nth root of absolute value of an equals to L is less than 1, the series is absolutely convergent and therefore convergent. B, if limit as n approaches infinity of the nth root of absolute value of an equals to L is greater than 1, or limit as n approaches infinity of the nth root is equals to infinity, then the series is divergent. And then number C, if limit as n approaches infinity of the nth root of absolute value of an is actually 1, then the root test give no information. On the convergence or divergence of this series. So an example, test the convergence of the series test for the convergence of this series. So solution, we know that our an is given by 2n plus 3 over 3n plus 2 power n. Now the nth root of an will be given by 2n plus 3 over 3n plus 2. So therefore limit as n approaches infinity of the nth root of an equals to the limit as n approaches infinity of 2n plus 3 over 3n plus 2, which is the same as limit as n approaches infinity of 2 plus 3 over n over 3 plus 2 over n, which is 2 over 3. And since 2 over 3 is less than 1, then the given series converges by the root test. Good. Now, we have given many tests on convergence and divergence of series. But then the question will be now, how do you know how to behave when you are given a question? Because there are many types of tests that you need to know before you determine whether the series is convergent or divergent. So let's give you some small tips that can help you to know how to behave when you are given a series and they want you to determine whether it converges or diverges without specifying the test that you need to use. So then now, so we know that, so summary, so I can actually call it the strategy for testing series. So these tools might be useful to help you to easily determine the convergence or divergence of a given series. It is not wise to apply a list of tests in a specific order until so that tool and effort. So instead, as with integration, the main strategy is to classify according to its form. So one, if the series is of the form it is a P series which we know so that's what we know. So that's when in the series of that form, then you know that you need to apply the P series test. And then number two, if the series has the form or it is a geometric sequence, geometric series, which converges if absolute value of r is less than 1 and diverges if absolute value of r is greater than or equals to 1. And then on this, for sometimes it might not be obvious for it to be of this form, two forms. So algebraic manipulation of the series that you have can allow you to express it in this form. So some will be required to bring the series into this form. Good. So let's see another different form, 3. If the series has a form that is similar to a p-series or a geometric series, then one of the comparison tests should be considered. In particular, if an is a rational function or algebraic function, of n involving roots of polynomial then the series should be compared with a p-series. Notice that the comparison test apply only to a series with positive terms but if has some negative terms, then we apply the comparison test to good. Number 4, another strategy. If you can see at a glance that limit as n approaches infinity of an is not equals to 0, then the test for divergence should be used. Number 5 strategy. If the series is of the form or then the alternating series test is an obvious possibility. Number 6, series that involve factorials or other products, including a constant raised to the nth power, are often conveniently are often conveniently tested using the ratio test. So bear in mind that approaches 1 as n approaches infinity for all p series, and therefore all rational or algebraic functions of n. Thus, the ratio test should not be used for such series. Number 7, if an is of the form bn raised power n, then the root test may be useful. Number 8, if an equals to f of n, where is easily evaluated, then the integral test is effective, assuming the hypothesis of this test are satisfied. Remember, the hypothesis was that the function must be decreasing in the intervals 1 to infinity. So in the following example, so those are some of the strategies that you can use. So in the following examples, we do not work out all the details, but simply indicate which test to apply. So example 1, if we have this series, then since an approaches a half, which is not 0, as n approaches infinity, we should use the test for convergence. Test for divergence. We already gave the statement for the test for divergence. And then number 2, now for this case here, since an is an algebraic function of n, we compare the given series with a p series. And then number 3, so before we go to number 3, then we can give the specific comparison test that you need to use. So the comparison test is where Bn should be the square root of n cubed over 3n cubed, which is n 3 over 2 over 3n cubed. So we compare by that. Number 3, we have summation n from 1 to infinity n e raised power negative n squared. And then, so this one, since the integral (1 to infinity of x e raised power minus x squared dx is easily evaluated we use the integral test notice that the ratio test also work. And then next example 4, summation from n equals to 1 to infinity negative 1 raised power n power 3 over n power 4 plus 1 So since the series is it's alternating, we use the alternating series test. Number 5, summation n from 1 to infinity 2 power n over n factorial. Now we say since the series involves n factorial, we use the ratio test. Lastly, number 6, summation n from 1 to infinity 1 over 2 plus 3 power n. So since the series is closely related to the geometric series, we use the comparison test. So do as many examples on series test for convergence and divergence to be able to solve a question when the person setting the question doesn't specify the method to use. If you do practice, you'll be able to get the questions